Here are the required questions and problems for Chapter 4. We started off the assigned problems with question 6. Two equal forces act on two different objects, one with a mass that is 10 times as large as the other. So we have mass 1, which is kind of small, and we have mass 2, which is 10 times as big. And it asks if equal force acts on the two masses, will the more massive object, that's this one here, the more massive object, have a larger acceleration, an equal acceleration, or a smaller acceleration? Well, we know F net equals m times a. So therefore acceleration is F net divided by m. So if we apply the same net force is the same between the two, and mass gets bigger, then acceleration has to get smaller because it's F net divided by mass. So the bigger object is going to have a smaller acceleration. The more massive object will have a smaller acceleration. For question 7, we have a 3 kilogram block and a 6 kilogram block, and the 3 kilogram block is accelerating at twice the rate of the 6 kilogram block. So if the acceleration for the 6 kilogram block is a, the acceleration for the 2 kilogram block is twice as much, so it's 2 times a, or 2a. Okay, so we know that F net equals m times a, and it's asking, is the net force acting on the 3 kilogram block twice as large as that on the 6 kilogram block, because it's got twice as much acceleration? Well, let's find out. So F net for the first block is m, which is 3 kilograms, multiplied by a, which is 2 times a. And then the net force for the second block is m, which is 6 kilograms, multiplied by the acceleration, which is a. And we can see that 3 times 2 times a is 6a for the net force of the first one, and then we have 6a for the force on the bottom one. So the net force is the same on the two blocks. In question 8, we have two horizontal forces acting on a block, like I show here in this diagram, and it's asking if the object is accelerated horizontally. Remember, horizontal is left and right, like the horizon, it's flat. Vertical is up and down. So in order for there to be an acceleration, we know that Newton's second law says we have to have a force, a net force. Newton's first law says that there can't be a change in motion without an outside force. Newton's second law says the net force and acceleration are proportional. The net force acting on this block is equal to 0 newtons, because this force and that force are the same, but in opposite directions and acting on the same block, so they add to 0. F plus negative F equals 0 newtons. Since the net force is 0 newtons, the acceleration is equal to 0 meters per second squared. F net equals m times a. If F net is 0, acceleration is 0. Now, number 9 is dealing with the same block as in number 8, and it's asking, is it possible that the block is moving? Now, I told you in question 8 that the acceleration is equal to 0 meters per second squared. That does not mean that the velocity is 0. That just means that the velocity is not changing. So is it possible that it's moving? Yes. It is possible that it's moving with a constant velocity. It could be moving at 5 meters per second, 10 meters per second, or it could be moving at 0 meters per second and not moving. But it is possible that it's already moving and just not accelerating as it goes. Exercise 1 has a single force of 40 newtons acting on a 5 kilogram block, and it asks us what the acceleration is. And from the equation F net equals m times a, we can solve for acceleration equals F net divided by m. And the net force, since there's only one force acting on it, the net force is 40 newtons, and the mass is 5 kilograms. 40 divided by 5 gives us an acceleration of 8 meters per second squared. In exercise 4, similar to exercise 1, we're given some forces acting on a block of a certain mass. In this case, we have multiple forces. So the net force is going to equal the sum of all those forces. In this case, we have 80 newtons pointed one way, and then 5 newtons pointed the other way. So to find the net force, we take 80 minus 5 because they're opposing each other. One is pushing one way, the other is pushing against it in the other direction, giving us a net force of 75 newtons. And we know the mass is 3 kilograms. Just like in question 1, exercise 1, it's asking for the acceleration, and solving the F net equals ma equation for a, we end up with F net divided by m, or 75 newtons divided by 3 kilograms, which gives us an acceleration of 25 meters per second squared. Exercise 7 gives us, again, two forces acting on the block, a 50 Newton force to the right, 30 Newton force to the left, and it tells us that there is an acceleration. So looking at exercise 7, that block from the diagram is accelerating at 4 meters per second squared. And we're asked to find the mass of the block. If that's the case, we have those forces and that acceleration. What is the mass in kilograms? All right, so we can first of all figure out what the net force is by taking 50 newtons minus 30 newtons. That gives us a net force of 20 newtons, and it's 20 newtons to the right in this case. And we know that F net equals ma, and we can solve for m equals F net divided by a, or 20 newtons divided by 4 meters per second squared, which gives us a mass of 5 kilograms. 5 kilograms. In exercise 10, we have a mass of 40 kilograms. And we want to know what the weight is. Weight is the amount of pull. It's the force that gravity pulls down with. And a special case of F equals ma is weight equals mass times the acceleration due to gravity. So we can actually do this two different ways. It doesn't say which g to use, so either one is fine. So it's either 40 kilograms times 9.8 meters per second squared, which equals 392 newtons, or, and I would still give credit for this, 40 kilograms times 10 meters per second squared, which would equal 400 newtons, and then either one of those is acceptable. In exercise 18, we have a mass. It says a ball. I drew it as a square, but you can imagine it's a ball. There. Now it's a ball. It's hanging from a string. And it says the ball has a mass of 1.5 kilograms. And it's receiving an upward force from the string of 18 newtons. And we're given two different parts to this question. Part A is asking what the net force is acting on the ball. A is asking for F net is some number of newtons. Well, let's look back at this picture. The ball is feeling a force up from the string, but it's also feeling a force down from gravity. That's equivalent to its weight. Remember, weight is the force that gravity pulls with. So weight is equal to m times g, and it's one of two things depending on which g you use. So it's either 1.5 kilograms times 9.8, which is equal to 14.7 newtons, or it could also be 1.5 kilograms times 10 meters per second squared, which is equal to 15 newtons. And depending on which one of those you used, the net force is going to be either 18 minus 15 or 18 minus 14.7, and that's going to equal either 3.3 newtons if you used this one, or 3 newtons if you used this one. All right, so we have a net force. And that net force is upwards because this 18 newtons is bigger than either of those weight measurements, which means we have an acceleration. And part B is asking what is the acceleration. And recall, acceleration equals F net divided by m. So we have either 3.3 newtons if you use 9.8 as your g, divided by 1.5 kilograms, which is equal to 2.2 meters per second squared. Or if you used 10 as your g, it would be 3 newtons divided by 1.5 kilograms, which is equal to 2 meters per second squared. All right, synthesis problem number 1 gives us a constant horizontal force acting on an object of 30 newtons and a 5 Newton frictional force pulling against that, and the mass of the block that's being pulled is 5 kilograms. And again, it gives us a few different things to answer. First of all, it's saying what is the acceleration of the block, and from previous problems you will recall acceleration is net force divided by mass. What's the net force on this? F net is going to equal the force to the right, which is 30 newtons, minus the force to the left, which is 5 newtons. So net force is 25 newtons. So we end up with a net force of 25 newtons divided by a mass of 5 kilograms, which equals 5 meters per second squared for our acceleration. Part B is asking us to remember some of what we learned in previous chapters, because it's asking if the initial velocity of the block is equal to 0, how fast is it going after 3 seconds? So if time is 3 seconds, if the velocity initial is 0 meters per second, it's asking what is the final velocity at the end of those 3 seconds. And if you remember back to the previous chapter, final velocity equals initial velocity plus a times t, which is going to equal 0 meters per second plus 5 meters per second squared, times 3 seconds. So we end up with 0 plus 5 times 3, or a final velocity of 15 meters per second. And lastly, in part C, it's asking us how far does it travel during that amount of time. And again, you'll have to recall that distance traveled for an accelerating object is v initial times t plus 1 half a t squared. V initial is 0, so that term goes to 0. So the distance traveled is going to equal 1 half times the acceleration, which is 5 meters per second squared, times 3 seconds squared. So half times 5 times 9 gives us a distance of 22.5 meters. And that's it.